A fundamental component of 5G new radio, and also one of the greater challenges of 5G deployments, is network synchronization. Precise phase and time synchronization of the base stations at the edge of the network is crucial for 5G radio performance, and disruption to timing synchronization will negatively impact data capacity, coverage, and the end user experience. It is expected that standard 5G TDD networks will require a network-wide delay of no greater than plus or minus 1.5 microseconds end-to-end. That is between the clock and the radio unit. Cooperative radio techniques like carrier aggregation, beamforming with massive multiple input, multiple output, MIMO antennas will require much tighter synchronization when deployed, with a level of accuracy below 130 nanoseconds for radio units on the same cluster. In practice, precise phase and time synchronization is obtained with a combination of technologies, such as PTP or IEEE 1588 version 2, where only a few centralized PRTCs or ePRTCs distribute time to the edge of the network via packet. These technologies almost always use the same primary source of timing information, GNSS. With an ever-growing number of GNSS signals in the sky, it is key to ensure the PRTC provides correct reference time when predictable but infrequent GNSS system events happen. These could include leap years, leap seconds, and GPS week number rollover. But assessing the network synchronization in these normal and predictable operating conditions is not enough. As has long been clear in industries that have traditionally relied heavily on GNSS, it is not a flawless system. System robustness has limits, and GNSS vulnerabilities are an increasing danger. Both individually and collectively, these vulnerabilities can have a considerable and even catastrophic effect on performance. Interference is a key consideration. For instance, nearby network antennas operating in bands adjacent to the GNSS spectrum can affect PNT performance. And whilst illegal in many countries, jammers, particularly in busy urban areas, present interference risks. Multipath and obscuration are common issues, especially in dense urban areas. Deploying more radio units is a challenge when GNSS reception can be prevented and affected by the signal reflecting and diffracting on buildings and other tall structures. Atmospheric interference is a constant but not consistent issue. Interference caused by solar storms can disrupt GNSS signals as they travel through the ionosphere. In addition, dense electron structures in polar and equatorial regions can cause significant delays. It's not possible to remove these threats, but it is very possible to mitigate the effect that they have on your systems. Whether you are developing, integrating, or using a PRTC, the only way to consistently avoid errors and disruption is via scientific testing.